one. So, here we have a picture hanging up. Suppose that A and B are the forces of tension of the two cables hanging the picture up. These forces are both 50 newtons, and the angle each cable makes with the horizontal is 30 degrees. How heavy is the sign? So, in this kind of question, whenever you see something about heaviness, weight, mass, anything like that, always think F equals ma, right? Because that is the only formula that you actually can use that it has mass in it. So we always know we're going to have to use that. And then we know the angle each cable makes for the horizontal is 30 degrees. How heavy is the sign? So what we're firstly going to do is draw a diagram. So this is 30 degrees. 30 degrees. And then forces are both 50 newtons. So the lengths here are 50 newtons. Now, we want to figure out how heavy the sign is. So we know that we need to include F equals ma somewhere. So let's have a think about this. We want m as the unknown. We know that a, the acceleration acting on the object, on the picture frame, is going to be acceleration due to gravity, right? Because that is the only acceleration acting on the object. So we know that, which means we need to find the force, and then we will have an equation with an unknown m that we can solve for. And this is the plan that we have so far. And looking at our diagram, what we can do is find our force that is acting in the vertical plane, because of course our acceleration is acting in a vertical plane, so our force needs to be acting in a vertical plane. What we can do is add these two together and see what we end up with. So there are two ways that you could do this. You could either add the components, the I and J components of these two, or alternatively, and this is my preferred method, you can just move the vectors around and do some vector resolution. So I might actually do that just because it is, in my opinion, like, I guess it's a little bit less arduous, right? And it's a little bit more fun. So here's our diagram that I drew just before. Let's go ahead and change the where the vectors are. So what we're going to do, remember, whenever we're adding vectors to find our net force, we need to add them head to tail. So I'm actually going to slide this vector, that one on the right, I'm actually going to slide it down to here so that our vectors are added head to tail. And as you can see now, our net force is going to be here. And that's going to be acting in the vertical plane. Now, what we need to do is find the length of that net force. And we're going to need to do some trig. So the first thing we need to know is, we have our two sides. and we have our unknown length, which means we're going to need to use our cos rule, if you're remembering correctly from methods. So remember, we use our sine rule when we have a side angle pair, and our cos rule when we have three sides in an angle. So we have three sides. We just need to finish off this angle. So hopefully you guys remember our angle rules. If you remember this one here, right? If you have these two lines crisscrossed over, the angles between them will be the same. So this tells us this angle in here is actually 30 degrees. Because our dotted line and I'll draw it up for you, our dotted line here and this line here act as our two lines here. So this tells us that our angle is still 30 degrees, right? So all we've done is we've just kind of taken this vector, slid it down to add it head to tail, gotten this angle, and now we can do our vector resolution. Again, you could definitely do this just by finding the I and J components. I really don't find that half as much as fun. But I might quickly go through an example of how you could do that once we've gone through this. Alright, so finding our net force, we're going to use our cosine rule. So we're going to have 2 times 50 squared, take 2 times 50 squared cos 60, and this gives us that our net force is equal to 50. So you could kind of tell that this was going to be the case, of course, because we have an angle of 60 degrees in between two sides with equal length, which tells us that it's going to be an equilateral triangle, right? So it's going to be 50 newtons, and this is going to be upwards. So this is the force exerted by the string. Right. Now we're going to apply F equals ma. So the force required to hold the picture up is 50. Our acceleration is 9.8 meters per second squared. That's just a number that you're going to need to remember. If you're not familiar with it because you're not in physics or you're just not familiar with it, I'm not sure if it's in the formula book. I'd have to have a look, but if it's not, make sure you remember that. So this gives us a mass of about 5.1 kilograms. Remember, the units for whenever we're using F equals ma is kilograms. So, as you can see here, what we did is we started by drawing a diagram, and then of course recognizing that we needed to find how heavy the sine was. We knew that we needed F equals ma, and then working on from there, we knew we needed to find the net force because we had A. So we found the net force using vector resolution and then solved for M. I'll quickly show you guys how you can actually do this without using the vector resolution and just adding up the I and J components. So what you could have done is the I component would have been the sine, so you would have had 50 sine 30, and your J component would have been 50 cos 30. So we know that it's sine and cos, of course, because our I component is always sine and our our j component is always sine and our I component is always, I wrote that the wrong way around, didn't I? Our I component is always cos and our j component is always sine. So it's j, this is I, and that's just from like the unit circle, right? So again, you could draw it out here. If this is our j and this is our I. So our resultant force is going to be the addition of these two j components and the subtraction of the two I components. Of course, because the I components are both being pulled away from each other, but the j components are both being pulled upwards. So our total j components is going to be 2 times 50 sine 30, and our I components will be 0. This is for our net force. So this is exactly what we got in using our vector resolution. Of course, because we only got our force acting vertically, not in a horizontal direction. Alright, so yeah, feel free to use either the components method or the vector resolution method, depending on what you're more comfortable with. Alright. Now we have a harder example. So now we're getting onto a harder example, and this is where we have an object on an inclined plane, right? So in these questions here, what we want to do is we want to rotate the axes to make things easier for ourselves, and you can see that's what we've done here. So assuming that the mass is equal to 200 kilograms, we need to find F in terms of mu so that the object can stay at rest on the ramp or move up at a constant velocity, right? So let's start with this question, right? So when the object is at rest, right, it means that the net force is equal to 0 because the applied force up the ramp is holding the object there against the friction and the force due to gravity, right? Or if it moves up at a constant velocity, we can also determine that using our F equals ma formula. So the information that we know is that the mass is equal to 200. Our angle is 30 degrees. And we know that F of friction plus F due to gravity is equal to the force, the applied force up the ramp, because our forces are balanced, leading the object to stay at rest, right? So our force due to friction is mu times n, where mu is our friction, and n is our normal force, right? So, what is our normal force? Remember, our normal force is this arrow perpendicular to the surface. It's the force that the inclined plane is pushing up against the object with. All right. So we need to figure out how we can find our normal force and our force due to gravity. So we can find our normal force using our trig ratios and our theta. So quickly drawing this on a right angled triangle, where this is 30 degrees, of course, because these two lines are parallel. So this gives us 30 degrees here. We know that our normal force is going to be equal to mg mg cos theta. And that is our normal force. And then our force due to gravity, the component acting down the plane, is going to be mg sine theta. Of course, because like this length here is mg, so our normal force is going to be the this length here, right? And our force down the plane is going to be that one there, is equal to our applied force. All right. Now this gives us our F in terms of mu. We can sub in our theta value. So of course, theta is 30 and M is 200 and G is 9.8. So we're going to have mu times, and then we can factorize out the mg, so we're going to get 0.866 mu actually simplifying this even further, this gives us 1697 mu plus 980 equals F. Alright, and this is our force in terms of mu, in order for the object to stay at rest on the ramp. For our object to move up the ramp at a constant velocity, we must have a greater force. So for it to move up the ramp, the force must be greater than the answer we covered just down here. All right. So, obviously, looking at our question from right here, um, what we did is we essentially rotated the axes, right? We didn't consider these axes tilted. We kind of rotated them and looked at them with respect to our inclined plane instead of with respect to the ground, which gives us a lot more um, ability to work with the just going through the slides to work through the question. All right, here we just have a few tips for concurrent forces. So remember to always draw a diagram and label all of the forces with directions and angles. If it's a flat surface, no orientation change needed. If it's on a ramp or an inclined plane, usually helps to set our I and J so that I is the same as the plane of the ramp. This probably isn't the only type of vector resolution question you'll get, but it covers most of the fundamental principles. Alright, now we are getting onto the second part of this modeling motion section. So here we need to consider and solve problems involving motion in a straight line with both constant and non-constant acceleration, including simple harmonic motion, and using our expressions for acceleration. So, here we have a few different expressions and equations for acceleration, and these are given to you on your formula sheet. So, if we are given a in terms of x, we need to use the equation a is equal to d half v squared on dx to get v squared in terms of x. If a given in terms of v, use either a equals v dv dx to get x as a function of v, or we can use a equals dv dt to get t as a function of v. So, this is a lot to remember. Probably use this slide as a guide when you are practicing, but otherwise try to just use your intuition more so. Alright, here we have a question here. So we have a particle being projected upwards with an initial velocity, an initial velocity of u. The air resistance on the particle is 7 mv squared. So we need to find the maximum height that the particle reaches in terms of u. And we first need to draw a diagram of what we know. So, let's start with our diagram and our force equation. So, we know that our particle, is being projected upwards vertically, right? This is our particle, and then presumably it's falling back down vertically. We know that our net force is going to be the force of gravity, which is pulling it down, minus 7mv squared. Okay? So this is going to be the force on the particle. So, negative mg. acceleration experienced by the particle. So, our G is of course going to be 9.8, and our F net is going to be MA. So let's find A. Of course, our M's are going to cancel out. And 9.8 minus 7b squared. And we are not going to be left with anything there. Alright. Now, since we want the height reached, we need to find x, right? Because that tells us the position. So, we have A, and this A that we have is a function of V. So, since we have A as a function of V, what we want to do is we want to use one of our acceleration equations with A and V in it, and x, so that we can solve and find x, right? So, out of the equations, what I'd like you guys to do is have a look at the equations given on your QCEE formula sheet for your acceleration equations. And the one that you might notice that is best is v dv dx equal to a, because this one includes a as a function of v and also x. Now we can pop in the formula just we came up with, which was negative 9.8 plus 7v squared. And now we can use this to find x. So we're going to take this v over to the side. So we're going to have dv dx equals negative 9.8 plus 7v squared over v. Now to get x, we need to integrate, right? But we have dv dx. When this isn't what we want to isolate x. We don't want to integrate with respect to x. So we're going to use our good old trick of inverting, right? So if we invert these two, we're going to get dx on dv. We're just swapping around both these fractions, equals negative v over 9.8 plus 9v squared, right? Now what we can do is we can integrate this with respect to v. So we're going to get that x is equal to the integral of v 9.8 plus 7 v squared dv. Alright, so integrating this, all you would need to do is use some simple linear substitution, and we would get an answer of negative 1 on 14 ln 9.8 9v squared plus c. So, now this tells us about the position of the particle with respect to direction because our particle is projected upwards. That just means our velocity is equal to 0. And we also know that at x equals 0, our initial velocity was u. So we can use that as well to find our c value. So, we know that, I'll just run out, I've got too far. So, we know that when we have u equals v, right? Because that is our initial velocity. When x right? So we know that our initial velocity is u, right? So we can put this into our formula now. So we know from there that our c value is going to be 1 over 14 ln 9.8 plus 7u squared. Right? So subbing this in to our original formula, this gives us that x is equal to negative 1 on 14. This is just the formula that we got before. Then plus our new c value. Now we can just combine these two ln's together using our simple log laws and take that 1 over 14 out the front. And this leaves us with 1 over 14 ln of 9.8 plus 7u squared over 9.8 plus 7v squared. Right. Now that we have done that, all we need to do is recognize, as I was saying before, that our maximum height occurs at v equals 0. So we can just get rid of this last part here, because that would be when v equals 0. And this gives us our